All right. Hi, everyone. Welcome to lecture 15. In this lecture, we're going to go over some more theory that involves kind of these general metric spaces like what we talked about in, at least it was section 13 in the book. I think that was lecture 8, if I remember correctly. So yeah, we're going to kind of continue that discussion now that we've defined the concept of continuity. If you remember, when we defined convergence, at first, we just defined it for sequences of real numbers. And then when we got to metric spaces, we were able to generalize that idea for sequences of points in a metric space, right? And actually, you should almost, sort of, well, not immediately realize, but it should seem sort of the path should seem relatively clear to you if you remember how we did that towards generalizing the concept of continuity for functions between metric spaces, in particular because the definition of continuity that we used really just boiled down to the definition of convergence for sequences. That was where, the way we defined it, it was just like for any sequence, sort of any convergent sequence of points in the domain with a particular limit, the values of the function also formed a convergent sequence, right? So we kind of packaged up all the real substance in the idea of continuity into the definition of convergence of a sequence. So if we were able to generalize that definition, we should definitely be able to generalize the definition for metric spaces. Actually, what's a little bit more interesting, though, is to, instead of just generalizing the sequential definition, which is like almost trivial, the way the book does it and the way I think is best to do it is to actually generalize the epsilon-delta properties. So if you remember, with continuity, we were able to take the sequential definition and show it was equivalent, right? So let me just start writing some stuff down. So for, so convergence of sequences, oops, we had, R, and then, the absolute value, I guess absolute value of b minus a or something, and then we generalize that to an arbitrary metric space with an arbitrary metric d. Right here, we had this whole long thing about there exists exists a capital N, or it was like for every epsilon there exists a capital N. I'm just gonna not even write all that stuff, but we had Sn minus S less than epsilon, right? Is the ultimate condition that we wanted to verify. And then in this case, what we ended up with is we ended up with just d Sn S less than epsilon, right? So we were able to, that's one way of generalizing the definition of convergence. So with continuity, so continuity of functions, one possibility you'd have, in the case of functions from R to R, you'd have, xn approaching a, roughly speaking, right, means that f of xn approaches f of a, right? And then in the context, right, now what we would like to do is generalize it to functions that map one metric space to another metric space, right? So S and S star are now metric spaces with their own metrics D and D star. And in this case, well, I guess maybe I should be careful with the squiggly arrow. So this here, what we were saying is this implies this, right? So then in this case, we could just say, well, Sn approaching, S implies f of Sn approaching f of S, right? And of course, there's like a bunch of other hypotheses in this definition, and you just kind of copy all of those over to this one, right? Where you're looking at, the domain of F. So like all sequences in the domain of F converging to A have this property or something like that, right? So you could generalize it that way. Or let's say another possibility you know, would be, let me see if I can kind of fit it here. So we would have, for functions f from R to R, we have the epsilon-delta property, right? So for all epsilon, there exists a delta, yada, yada. In the end, we have f of x minus f of x naught. Well, actually, the yada, yada is kind of important in this case. There exists a delta such that for all x in the domain of f with absolute value of x minus x naught less than delta, we have this is less than epsilon, right? Now for a function between two metric spaces, we can do the same trick we did here, right? Which was we take instances of the absolute value metric, right? The Euclidean metric on R, and then just replace it with a generic metric, right? So we can take this situation and we would say all this, for all epsilon, there exists a delta, et cetera, such that for all x in the, or for all s or something, you know, I don't know, it doesn't really matter what letter you use. I'll just use x again, honestly. So for all x in the domain of f, which is now a subset of s, so for all x in the domain of f, now instead of this condition, we'll have d of x naught less than delta. We have d of f of x naught is less than epsilon. Okay, so it's a little bit cramped, sorry. But yeah, so this is what we end up doing. Okay, so the definition for metric spaces of continuity is actually phrased in terms of the epsilon-delta property. But of course, you could equivalently phrase it this way. So let me just write the definition down, you know, more carefully than this, obviously, just for the record. So let's say let S D and S star D star be metric spaces and F from S to S star a function. We say, okay, they use S and S naught, so I'll just use that. We say F is continuous at S naught in the domain of F, which is of course a subset of S, if for all epsilon greater than 0, there exists a delta greater than 0 such that in this case, okay, actually, sorry, I should be consistent with the book here. In this case, we actually consider the entire metric space to be the domain of F. So the reason we do this is because with R, we want to allow the domain of the function to be like a proper subset of R, just because there are a lot of functions defined only on special subsets of R that we're actually interested in analyzing. But in this case, because we're dealing with an arbitrary metric space, it doesn't make sense to allow the domain to be a proper subset of the metric space, because then you could just treat the domain as its own metric space, basically, right? If you have any subset of a metric space, you can kind of ignore the ambient metric space and then just consider the subset as an entire metric space in its own right, and everything then, and that's all that really matters. So you can just do that. And so then in that case, you can sort of assume without loss of generality in this picture that we've already made that restriction, so that S literally you can say is like sort of defined to be the domain of F as a metric space, right? Or something like that. So we actually consider S as, yeah, and this notation actually requires S to be the domain of F. This notation wouldn't make sense otherwise. So F is defined on all of S. So that's why we can say for all X, or for all S in S with the distance between S and S naught less than delta, we have the distance between F of S and F of S naught is less than epsilon, okay? And similarly, for uniformly continuous functions, we would say, F is uniformly continuous on a subset E of S if, and now we say for all epsilon greater than 0, there exists a delta greater than 0, such that for all S in S, or sorry, for all S in E now, or really actually for all S and T or something, yeah, S and T in E with distance of S and T less than delta, we have the distance between F of S and F of T is less than epsilon. All right, so as you can see, we've just sort of systematically, followed this pattern of taking the definitions we had before and replacing the Euclidean metric with a generic metric and ending up with a definition that applies to functions between two arbitrary metric spaces. So just to cap this off, let me kind of list off a few notable examples, right? So the first example is, of course, if S D S star D star is R with the Euclidean metric, then the generalized definition reduces to the old definition. Okay, so our original definition of continuity, a function from R to R with Euclidean metrics in both spaces is continuous according to definition 21.1 if and only if it is continuous according to whatever, 19.1, yeah. Right, so that was our original definition of continuity. And of course, actually, this is also true if S and S star are subsets of R with the Euclidean metrics on those subsets. So it's actually doesn't have to be all of R. But yeah, just as an example, if you have a function that's defined on all of R and it takes real values, then if it's continuous according to the original definition, it's also continuous according to this one and vice versa. Okay, so we would like, that's important. We want to see that because that means that our definition really does make sense as a generalization. Okay. Another example would be just, functions from, R to the K to R with Euclidean metrics. So something like, you know, f of x1, x2 is x1 squared plus x2 squared. F of yeah, I don't know, x1, x2, x3 is x1, x2 plus x1, x3, or like plus x2, x3, or whatever, right? Any kind of sensible looking expressions in terms of some finite number of variables like this will end up being continuous. It's a little bit of a task to prove something like that, but you know, you can formulate some fairly straightforward general theorems about when a function of multiple variables like this is continuous. It's really not that hard. And yeah, but like, as a rule of thumb, if you just write down a reasonable expression, especially expressions that only involve like addition and multiplication, so polynomials and multiple variables are automatically continuous and so on, right? Or as another example, which we'll look at a little bit more actually, functions f from R, now from R to say RK, with again Euclidean metrics. These are called paths in RK. You might also have heard the term from, you know, vector calculus, parametric curves, because the idea is, right, I mean, what do these functions look like? They look like, you know, f of t equals like f1 of t, f2 of t, right, and so on, fk of t. So you have like k coordinate functions. By definition, that has to be the case. And, you know, it'll turn out that f of t is continuous as a map of metric spaces if and only if each of these coordinate functions is continuous. Just like with the definition of sequences, right? We looked at sequences of points in RK, and we showed that a sequence of points in RK converges if and only if each component sequence converges independently, like individually, right? The same thing is basically true for parametric curves or paths, which is, I think, the preferred terminology that I'm probably going to stick to is paths. So yeah, these are paths in RK, and so if, you know, if k equals 2 or 3, we can actually visualize f of R, the image, right? Not the graph, not to be confused with the graph of f, which actually has one extra dimension where you plot the t coordinate itself, right? But if you ignore the t coordinate and just look at all the values that you get out of this from plugging in all the t values, then the image of the line, of the real line, actually becomes like a curve in space, right? So as a curve in RK. So, you know, for example, oh, they usually use gamma. Sorry, let me switch to gamma. Yeah, let's say, okay, I'll just say gamma for all of these. Okay, so gamma, all gammas. So let's say gamma of t is like a cosine of t, b sine of t. You've probably seen this in Math 53. You end up with, you know, an ellipse whose, you know, width along the x-axis is, I believe it should be a, Yeah, and then the height along the y-axis is b, right? Or the total width is 2a, and the total height, or the it would be 2b, I guess, right? Or gamma is t, t cosine of t, sine of t, something like that. Then you would end up with let's see. Oh, I guess they do it a little bit differently, but I guess in this picture, if this was the x-axis and then this was, let's say, the y-axis, and then this was the z-axis, you'd end up with something like it's a helix which spirals around, spirals around the x-axis in this case, right? So you can get all sorts of weird stuff with different combinations of functions, and yeah, we'll talk a little bit more about paths. We won't do a whole lot of sort of geometric analysis of paths, but they do play sort of an important role in topology, because there's a concept of path connectedness that basically relies on paths as a way of characterizing the topological structure of a space. Anyway, so that is, I believe, yeah, that's it for this video. And then in the next one, I'll actually go ahead and prove this claim I made about continuity of a path or of a parametric curve function like this being equivalent to the continuity of the individual component functions.